Hello everyone, welcome to Aaron. So now we are going to solve this question based on digitally. It has been given that the compression ratio is 16, the initial, the pressure and temperature values are given, and the heat added is given. And we have to find the cycle efficiency. So let us see how we can find it. So if you know the formula for cycle efficiency, you will get like what we have to do in this question. So let us first write the cycle efficiency formula. We have cycle efficiency as 1 minus 1 divided by 5 to the power gamma minus 1 into 5 to the power gamma minus 1 divided by the into alpha minus 1. Alpha is the cutoff ratio. Gamma is the isentropic coefficient. And R is the compression ratio. So we have the compression ratio given for in the question. We have the isentropic coefficient, which we can take it as a 1.4 for air because it is an air standard efficiency. So we only need to find the cutoff ratio here. This is unknown. So we will need to find the cutoff ratio in order to solve this question. Let's see how we can find cutoff ratio. So if you define cutoff ratio, what is the definition of cutoff ratio? So cutoff ratio is nothing but the ratio of volumes after the combustion and before the combustion. So if you look at in a diesel cycle, so let us say this is a typical diesel cycle. 1, 2, 3, 4, P, V. We know that the 2 to 3 is a constant pressure heat addition process. QS will be added there. 4 to 1 is a heat rejection process. And 1 to 2 is nothing but isentropic compression process. We have the compression ratio is nothing but this V1 divided by V2 will be the compression ratio. And we also have the temperature and the pressure at point 1 given. We need to find the, let us say, cutoff ratio. So cutoff ratio is nothing but the volume after the combustion divided by volume before the combustion. So in our case, it will be V3 by V2 because the process 2 to 3 is where the combustion will be taking place and it is a constant pressure combustion process. So it will be V3 divided by V2. And we need to find V3 divided by V2. So, but if you look at the process, it is nothing but a constant pressure process. So for a constant pressure process, if you apply the ideal gas equation, you will get it as a PV is equal to RT. And if you calculate pressure, which is nothing but RT by V, and if you take it as constant, because it is a constant pressure process, then you will get it as RT2 by V2 should be equal to RT3 by V3. And if you cut the R, you have T like V3 by V2 as T3 by T2. So what does it represent is nothing but V3 by V2 can be also calculated by T3 by T2. The ratio will be the same for a constant pressure process. So the cutoff ratio can be also calculated from the temperatures at point 3 and point 2. It is what we are like taking from this equation. So let us see how we can calculate temperatures at point 3 and point 2. For point 2, it will be very easy because you have the isentropic compression equation as P to the power gamma is equal to constant for pressure process 1 to 2, which you can convert for in the terms of temperature and volume. Like just write P is equal to RT by V. For ideal gas, you have T1 V1 to the power gamma minus 1 as T2 V2 to the power gamma minus 1. And you have T2 as T1 into V1 by V2 to become the compression ratio to the power gamma minus 1. So T1 we have 27 degrees Celsius, which will be 300 Kelvin into, so which is 16 to the power gamma minus 1 is 0.4. So 16 to the power 0.4 into 300 will become 1000.8. This should be 2008. 0.6. So this is how we can find T2 is 2008.6 Kelvin. Let us just calculate it once more, like 16 to the power 0.4 into 300 should be 909.42. Sorry for the calculation mistake. So this T2 should be 909.42 because the temperature was unusually high. You can just like fact check or backtrack your equation. If the temperature is unusually high, then you can just say that there might be some calculation mistake also. So the temperature at point 2 should be 909.4. And let us see how we can calculate temperature at point 3 now. We have heat added at constant pressure, which is Cp delta T for the process between 2 to 3. So Cp delta T should become 2500 kilojoule per kg as given in the question. And we also need to take the units of Cp such as kilojoule per kg Kelvin. So in that unit, the value of Cp for air is nothing but 1.005 kilojoule per kg Kelvin. Into delta T will be T3 minus T2 is equal to 2500. And we need to find T3, we have the value of T2. And you can just calculate this. We have 2500 divided by 1.005 plus 909.42. You have T3 as a 3396.98. So T3 will become 3396.98 Kelvin. So let us move ahead. After calculating T3 and T2, you can just calculate the cutoff ratio by just taking the ratio of T3 and T2. Because we have been proved, we have been proving, we have already proved that the V3 by V2 is already T3 by T. So V3 by V2, which is the cutoff ratio, should be equal to T3 by 2P, which is 3396 divided by 909.4. So it should be 3.73 as your cutoff ratio. So if you just put this cutoff ratio and the compression ratio and the gamma values in the original equation, we have 1 minus 1 divided by 16 to the power 0.4 into 3.73 to the power 1.4 minus 1. 1.4 into 2.73. So let us just calculate it with the 3.73 to the power 1.4 is 1 divided by 3.4 into 2.73 divided by 16 to the power 0.4. 1 minus that will give you 54.1 as your cycle efficiency. So this is how you can solve this question. So mainly if you look at your formula, there will be an unknown and you can just solve your question using like the technique that whatever is the unknown, try to find out and you can just put it in your equation and you can solve that equation. This is how you can solve this equation or the question. Thank you.